Hey, in this lesson, we're going to look at areas, and we're going to escape antiderivatives for a little bit with these areas because we're only going to do area approximation. Before we get into areas, I need to talk a little bit about the terminology of areas. And when you're dealing with areas, we'll use the phrase area under the curve, and all that means is area between the curve and the x-axis. So for this problem right here, if I wanted to find the area under this curve, this part right here, I'll be finding this area. That's the area we're talking about. For this one, the area under the curve, even though it's above, we're actually finding the area between the curve and the x-axis. So when we say area under a curve, it literally means, it really just means the area trapped between the curve and the x-axis. So keep that in mind. And the next thing, the way we're going to approach areas is through a technique called Riemann Sums, which really means we're just going to divide the area excuse me, into a bunch of rectangles, and then we'll find the area of the rectangles. Now, one thing that's going to be very important, and I hope y'all can remember this, but there's a formula that we're going to use in this, and this is pretty advanced, but the area of a rectangle is base times height. Y'all need to study that and make sure you remember that formula because it's crucial to Riemann sums, and if you can't remember that, then you're going to be up a creek. If you have problems with that, please come see me, and we'll work on that. It'll probably take about 30 minutes for me to explain that to you, so that's the area of a rectangle. And the idea behind Riemann sums is we will divide the region up into, I'll tell you how many areas to divide it into. So let's just say I divided this region into 4 subdivisions. I want to find this area. I wonder if my paint bucket's going to work. It was giving me fits earlier. It's probably not. No, I don't understand this program. See if it fills in my B. Did it? Can't tell. So anyway, say we divided this into 4 subdivisions and I wanted to use rectangles. What we do is we draw our rectangles up to the curve. And you have to choose whether you're going to use the left or the right side. So if I wanted to use 4 rectangles, I could draw my rectangles like this, such that the right side of the rectangle determines the height. So if I was going to estimate this area, what I'm drawing right now would be considered right-hand Riemann sums with 4 subdivisions, where the right side of the rectangle is determining its height. And we can find the base is just some change in x, so we have our base and we have our height. I could also do, that was left-handed. By the way, I'm stupid, I don't know my left from right. Those are left-sided, because for each interval I use the left side of the rectangle to determine the height. We could also do right-handed Riemann sums, which means the base is the same, but now I go up until the right side hits my curve. So in this case, my right-hand Riemann sums would look like this. And this is a right-hand Riemann sums. And then the last one that we're going to look at for now is called midpoint Riemann sums. So we can use the left side, we can use the right side, or we can divide this up so that the midpoint, the middle of the interval determines the height. So I would drag my rectangle up until the very middle hits the curve. So about there. Drag my rectangle up until the very middle is on the curve, about right here. So this is called midpoint Riemann sums, and we'll do one of those. We're going to do one of each in this lesson. So you have 3 different types of Riemann sums. You have left, right, and midpoints. And rather than go through a whole bunch of technical details with weird mathy formulas, I figured it would be easier simply to do this with real problems. So for this first example, I want to do left-hand Riemann sums, or left endpoints, and Riemann sums to estimate the area under this parabola on the interval 0 to 4. And notice I told you how many rectangles to use. I'm going to give you all of that information. Now, I'm a visual person, so I'm going to sketch an extremely rough graph of y equals x squared. And I mean extremely rough. My y equals x squared, I know it starts at the origin, and then it does something like this. So there's y equals x squared. I'm going to spread that out a little bit more and take up more of my graph space. There. So there's my y equals x squared. I know it looks something like that, and this is simply for a visual. Now, if I go from 0 to 4, 1, 2, 3, 4, and I use 4 rectangles, then each rectangle is going to have a base of 1. By the way, the base of your rectangle is whatever the change in x is, and your change in x is always your ending point minus your beginning point divided by the number of rectangles. In this case, A and B are 0 and 4. and n is also 4. So if I did 4 minus 0 divided by 4, that tells me that each rectangle is going to have a base of 1. And I'm using the left endpoint to determine the height. So when I draw these rectangles, my first base is going to go all the way to 1, and I raise up until the left side of my rectangle hits the curve. Well, for this first one, my rectangle is not going to go anywhere because the left side is going to hit at the origin, so we actually don't have an area for that first one. Now my second rectangle, I'm going to go from 1 to 2, and I go up until the left corner hits my curve. My third rectangle, I'm going to go from 2 to 3, and I'll go up until the left point hits the curve. Fourth rectangle, up until the left point hits the curve, and that's going to be our area approximation. And it's a bad approximation because there's a whole lot of area we're not accounting for in these little regions. So this is going to be a bad underestimate, but this is what we're going to do. So our area is going to be approximately, my first rectangle has a base of 1 and a height of 0. My second rectangle has a base of 1, and the height is determined by the curve. So if x is 1 and I go up to the curve, then my y-coordinate is 1 squared, which is 1. So the height of my next rectangle is 1. My next rectangle also has a base of 1 and a height of this point. Now this is an x-coordinate of 2. And if I plug 2 into my curve, into my equation, that's the ordered pair 2, 4. So the height is 4 plus, then my last rectangle, the left endpoint's at 3. And if I'm on the parabola x squared, that's the ordered pair 3, 9. So the base is 1, and my height is 3. And we get an area approximation of 0 plus 1 plus 4 plus 9, which is 14. A pretty gross underestimate, but that is what the estimate is. So that was left-hand Riemann sums for rectangles, and we got an approximate area of 14 based on those 4 rectangles. And there is a rectangle with 0 height right here. Let's try right endpoints. Let's say I have the function x cubed plus x. Now I'm about to do something that's probably going to blow your minds, and you're not going to like this. But where the curve actually is not going to make a huge difference in your setup. What I mean is, oh, that was a terrible thing to say. Now that's just confusing. What am I thinking? I really don't need to see my function. What I really need to see is my x-axis and how my x-axis is divided up. If I look at this function, I'm only going to look at my x-axis. So here's my x-axis, and I'm going from 1 to 3. So I have 1, 2, 3. I want to find the area between 1 and 3. So I'm looking between these x-coordinates right here, and I'm dividing it into 4 rectangles. If I divide that into 4 rectangles, then let's see, that'd be each rectangle is 3 minus 1, b minus a over the number of rectangles would have a base of 1/2. So my change in x, b minus a over n, is 1/2. So I'm going to go to 1.5 or 3/2. And then my next one will be at 2. Then my next one will be at 2.5 or 5/2. And we are using right endpoints. So I'm going to use 4 rectangles. So my rectangles are going to go up like this. My first one is going to be from 1 to 3/2. My next one is going to be from 3/2 to 2. My next one is going to be from 2 to 5/2. And my next one is going to be from 5/2 to 3. So I have 4 rectangles in that interval. Each of them have the same base, and I'm using the right sides to determine the height. So my first rectangle has a base of 1/2, and the height is going to be whatever my function is, my function's value at 3/2. So when I plug 3/2 into my equation, x cubed plus x, that will give you the height. My next rectangle has a base of 1/2 also, and the height is going to be wherever my function is at 2. So my next rectangle has a height of f of 2. My next rectangle, a base of 5/2. I'm sorry, a base of 1/2. They all have a base of 1/2, and my height is determined by 5/2. So it's 1/2 f of 5/2. plus, and then 1/2 is the base of my last rectangle, and the height is determined by my right endpoint, which is 3. So 1/2 f of 3. And I will let you use your calculator on problems like this. So I'm going to pause the video while I punch this in the calculator real quick. Go away. There. All right. And when you punch all that in, you get an area of 63 over 2, or if you're fancy schmancy and you want to use decimals, I'm okay with 31.5 because that is exact. So you can use the left point, you can use the right point, and you're just plugging those left and right points into the function to determine the height of each of your rectangles. I have one more example, and it's using midpoints with 3 rectangles going from 0 to 6, and my function, f of x, is going to be x squared plus 2x. I'll just rewrite it, x squared plus 2x. So I'm going to sketch out my x-axis and mark it up. So here's my x-axis. I'm going from 0 to 6. So I'll go 0, 1, 2, 3, 4, 5, and 6. And this time we're only using 3 rectangles, so my change in x is going to be b minus a, which is 6 minus 0 divided by 3, number of rectangles. And that gives you a change in x of 2. So each rectangle, if I go from 0 to 6 with 3 rectangles, each rectangle will have a base of 2. So my rectangle, my first one's going to go from 0 all the way to 2. My next rectangle is going to go from 2 all the way to 4. And my third rectangle will go from 4 all the way to 6. Now, y'all are smart enough, I'm hoping, that you don't have to use the formula to get it in these problems. But sometimes the b minus a over n will come in handy if we have some real bizarre change in x's or something like that. So my rectangles, my area is going to be, my first rectangle has a base of 2, and my height is, now in this case, remember we're using midpoints, so my height is determined by what's happening at 1. So my height is my function's value at 1, plus my next rectangle, base of 2, and my height is determined by whatever's happening at 3, because that's right in the middle of that rectangle. My last rectangle, a base of 2, and a height determined by whatever f of 5 is. And even though these are nice whole numbers and it wouldn't be too hard to work that out by hand, for the sake of time, I'm going to pause this and punch it in the calculator. You get 106. So you get an area approximation of 106 using midpoints and 3 rectangles with this problem. So real basic concept here, it's simply area of rectangles, and for each rectangle you have to determine the base and the height, and just be aware of whether your height is determined by the midpoint. In this problem it was the right endpoint, and in this problem it was the left endpoint. And you just simply add up all those areas. It is usually going to be a bad approximation, but this is what we're going to use for now, and until we learn some techniques to get more accurate answers.